Thank you very much, and congratulations to Professor Burns once more. And so, talk is on Rabinowitz Floer homology. And this Rabinowitz Floer homology is an infinite-dimensional example of Morse homology. So let me first briefly recall what is Morse homology and why one wants to study this. So Morse homology, let's start with a closed manifold and assume that we have some Morse function on it. So f is smooth function on x, Morse function, meaning that for all critical points of f, the Hessian is non-degenerate, so that's the Hessian of f, and then its kernel is just trivial. And given such a Morse function, we can cook up some Morse chain complex. So this Morse chain complex is given by is vector space generated by the critical points of f. We just take these critical points as a basis of as a Z2 vector space generated by critical points of f, and the grading is given by the Morse index. So grading by Morse index, which is just the negative, the number of negative eigenvalues of the Hessian counted as multiplicity. Number of negative eigenvalues of this Hessian counted as multiplicity. And then we have to define a boundary operator. So boundary operator so if we adjust, it's a linear operator, so I adjust the, so if x is a critical point of f, then the boundary of x, this is the sum over all critical points of this Morse function, where the Morse index is one less than the one of x, so that's the Morse index. And then we take the number of gradient flow lines from this critical point x to this critical point y, so that's a Z2 count. Gradient flow lines from x to y, so that's a linear map. And so let's, to understand what happens, let's just look at an example, the famous heart. So this is a picture, a little deformed picture of S2. As function f, we take the height function. So you see we have 4 critical points, here 2 maxima, and then here a saddle point, and finally here a minimum. And now what we have, so maxima, saddle point, minimum, And what we have to count are these gradient flow lines. So you see we have here a gradient flow line from this maximum to the saddle point, from both maximum, and then we have two gradient flow lines from this saddle point to the minimum. So this means that the boundary of x1 equals the saddle point, also equals the boundary of x2, and the boundary of y, this equals 2 times z, but since we work with Z2 coefficient, that's just 0. 2 coefficient. And in particular, what you see is that this E defined in this way is a boundary operator, so note that E square actually is 0. And as soon as we have D square equals 0, we can define Morse homology just by Hn star F, the quotient of the kernel modulo the image of this boundary operator. And if we compute what happens in this example, so in example we have the Morse homology of F. So you see in degree 2 the maximum are not in the kernel, but the sum of this is in the kernel. So the sum of this just generates the homology in degree 2. So we have here a set 2. Same happens in degree 0, where we have the minimum which is not in the image. So we have a set 2 in degree 0 and 2, and in degree 1 we have the saddle point, but the saddle point is in the image from the maximas, so we have here 0 else. And what you see is what we just computed in a bit funny way is the single homology of S2. And so that's this works in this way. That's not just in this example, but in general this is a non-trivial fact. So the fact is that if X is a closed manifold and F is a Morse function on this manifold, then the Morse homology, we can define this Morse homology in this way, and what we compute is just the singular homology of the manifold. In particular, what you see is that the answer what we compute is independent of the Morse function itself. So that's independent of F. And this has a nice corollary, this fact, namely that as a corollary, these are the Morse inequalities. Namely, the number of critical points of a Morse function on a manifold will be always be bounded from below by the sum of these Petty numbers. Yeah, so yeah, here I work with Z2 coefficient. You can also work with arbitrary, with Z coefficients, but then we have to count with signs. So I have to introduce signs. And the good thing about Z2 is that 1 equals minus 1, so we don't have to care about signs. So that's why I decided to use Z2 coefficients. So that's the corollary. So the critical points of F, this is bigger or equal than the sum of the Petty numbers of okay. And so Morse homology is kind of useful thing to detect critical points. So we have lower bound just in terms of topological data. And the purpose of Floer homology is to generalize this picture to infinite-dimensional setup. And what one is interested is these are periodic orbits. And so that's old question going back to Poincaré. So we have M omega, symplectic manifold, and we have a function on this symplectic manifold, which is called the Hamiltonian. And then to this function we can associate a Hamiltonian vector field, xh, Hamiltonian, which is implicitly defined by the condition that the one form d of h equals, if we plug in x of h into the two form omega, we get d of h. And the equation which explains the propagation of physical systems, so that's Hamilton's equation, is just dtx equals xh of x. And now for periodic orbits one asks how many periodic solutions of this equation exist. So now if you so how many do we roughly expect? So for a periodic solution we have to fix the initial condition. So we have the choice of dimension of the manifold, and after that then we have this ODE. Then this is determined, just given by the initial condition. Then after some time, so we have again an additional parameter. So we have to come back to the initial point. And so to come back to the initial point, that's like dimension of m equations. So roughly we expect a one-dimensional family of periodic solutions. But so to get the discrete problem, one has to put some additional constraint. And there are two points, two ways to put this additional constraint. So the first is the fixed period problem. So in the fixed period problem, in this problem, this h might actually depend on time additionally. So h might be time dependent, i.e., so let's assume it's periodic, so it's a function of m times the circle, and we abbreviate ht is just h evaluated at t as 1. And then we have some time dependent vector field, Hamiltonian vector field. And so we are interested in solution of so dtx dt equals xht xt, and xt plus 1 equals xt. So these are one-periodic solutions. And then the other problem is, instead of fixing the period, we can also fix the energy. So problem 2 is fixed energy problem. So in the fixed energy problem, we need that H is autonomous, or in other words, independent of time. Then just by preservation of energy, so preservation of energy, and H is preserved along its flow. H preserved along flow of its Hamiltonian vector field. And what we want to find are periodic orbits on a fixed energy hypersurface sigma equals H inverse of 0 of arbitrary period. So these are objects of interest, and to both of these problems we have some variational approach. We can interpret both solution of this problem as critical points for which we would like to apply some kind of Morse homology to detect them. So I have some variational approach, and so for simplicity I would like to assume that omega is exact, so that omega just equals d lambda, an exact symplectic form. We can, so the variational approach also works in without this condition, but requires some additional notation and work. So then for the fixed period problem, we have the action functional of classical mechanics. That's for problem 1. So we have this action functional. This goes from the loop space of M. So there's here the just smooth maps from the circle to M, the free loop space. And the critical point, so this functional, if I plug in a loop, then what I do is I just first take the area, I integrate lambda along this loop, and then subtract the action, the time-dependent action of this Hamiltonian along it, and the critical points of this action functional, these correspond precisely to the periodic orbits of period 1. And so that's for fixed time problem. Now for the fixed energy problem, there is another action functional which was first, so Rabinowitz used this action functional in his famous paper where he proved the first version of the Weinstein conjecture. It's Rabinowitz action functional. That's for problem 2. So this functional is from loop space times R to R. So what it looks quite similar to the previous one, and we also take, but it lives on a different space, so not just on loop space, but loop space times R. And what we do is, first we also take area, but then this eta, this real number, is, we can think of some kind of Lagrange multiplier. We plug this in front of this here, then this becomes the constraint. We have minus eta integral 0, 1 h et et. And then if we look at critical points of this functional, critical points, so that's as before, if we just differentiate with respect to the loop, we just freeze in the Lagrange multiplier, and we have just what we had before, so we have TTV minus eta xh of v equals 0. But then if we differentiate with respect to the Lagrange multiplier, we get the constraint. So we have integral 0, 1 h vt dt equals 0. But now you see, because h is time independent, autonomous, energy is preserved, so h is constant along this orbit, so this mean value constraint from the second equation is actually a pointwise constraint. So that's preservation of energy. So star is equivalent to equation star star, which is just ETV equals eta xh of E, and then h vt equals 0 for all t s1. And then up to reparameterization, this is just a periodic orbit on this fixed energy hypersurface of this Hamiltonian vector field, and if you reparameterize, the Lagrange multiplier eta will become the period. So that's so up to reparameterization. So this is a solution of star star. These are periodic orbits of xh on the energy hypersurface sigma inverse image of 0 of h of period eta. Okay, so we have we can interpret this solution as critical points. Now we have to build up some Morse homology. And so what Floer built this Morse homology in this first case, in the fixed period case. And so Floer was motivated by the following conjecture. It was Arnold conjecture. Namely, if m omega is a closed symplectic manifold and h is some periodic time-dependent Hamiltonian, then the number of critical points, these are the one periodic orbits, can be estimated from below by the sum of the Betti numbers under some non-degeneracy assumption, which corresponds to the fact that the Hessian of this functional is non-degenerate. So you should, of course, compare this conjecture to the, which now proved, is to the Morse inequality. So compare to Morse inequalities. And so Floer's approach to the Arnold conjecture was the following. So he also define Morse homology for this A of H, and so we have to count gradient flow lines. And yes? What's the meaning of eta? Eta is here is just a real number. You can think of it as a Lagrange multiplier. Since here we are looking at the fixed energy problem, and this Lagrange multiplier forces the critical points to lie on this energy hypersurface. Okay, so Floer wants to define this Morse homology, and so he has to come up with a gradient flow equation. So what's Floer's gradient flow equation? And here he was a bit bold, since this functional is kind of, here is on this loop space. You can think of, maybe you can complete them to W12 loops, but he didn't use W12 metric, but a much weaker metric, namely he used the L2 metric on this free loop space. So what he did is, so if J is almost complex structure which is compatible with omega, so omega compatible almost complex structure, meaning that if you plug this almost complex structure into omega, you get the Riemannian metric. On M, then the metric, yeah. Eta itself has then the meaning of the period. At the critical point, this corresponds precisely to the period of the periodic orbit. So we have Riemannian metric, and then we just integrate this. So if V is a loop, and then we have V hat 1, V hat 2 tangent vectors of the loop space, so just vector fields along V, then this L2 metric is just integral 0, 1 of omega V hat 1 t J Vt V hat 2t dt. And the gradient of AH with respect to this metric, that now becomes EA of H. This is just, if you compute this, that's just J of V dTV minus xh of v. And now gradient flow equation itself, he interpreted not so. You can think of gradient flow equation is kind of the flow lines on this loop space, but flow lines on the loop space you can also think as maps from the cylinder to the manifold itself. And he interpreted this gradient flow lines in this way. So the gradient flow equation, that's, so we have V is now a loop which flows, and we should just think of this as a map from the cylinder to M, which or we can kind of smooth map from the reals to the loop space, and which just satisfies DSV equals this gradient, or interpreted as a PDE. This is DSV plus JV dTV minus XH of V equals 0. And what you see here, what comes out is just kind of, if you ignore this Hamiltonian term, this would be just a holomorphic curve equation. So that's a perturbed holomorphic equation. And so a priori this idea of using this gradient flow equation to define a boundary operator as in a finite dimensional case was kind of bold idea, since to get the boundary operator one has to prove this crucial property that d square equals 0, and this crucial property translates to some compactness property of this equation. And but since this is basically a holomorphic curve equation, what Floer could use was the theory of holomorphic curves due to Gromov, and then using this Gromov compactness, he could see that using just solutions of this equation, you can define a boundary operator in this infinite dimensional setup as in the finite dimensional case I explained at the beginning. Here in the fixed period problem, h might depend on time. So the crucial point this is Gromov compactness for holomorphic curves. And so this compactness then translates into the fact that counting solutions of, let's give this equation a name. Yes, basically, up to this, this is a perturbation of the holomorphic curve equation. S, yes. So S is this real. J is the this almost complex structure, this omega compatible almost complex structure to define the metric. Yeah. Yeah. So this action function is a function on the loop space. Yes. Right. So we. Now h is below. If h is below, we have no eta. So as I told, we have two problems. We have the first problem is the fixed period problem. There we have no eta. Then that's what I explain now. But then we have the other problem where we have fixed energy, and for the fixed energy problem we have the eta. But still, we are still at the fixed period problem. So, but now we have this homomorphic equation, then we can count these solutions, and counting solutions of star gives a well-defined boundary operator. And if we have a well-defined boundary operator, so we have some Morse homology for this AH is well-defined. And that's now called Floer homology. Morse homology. And if we have this Floer homology, we get the Arnold conjecture. Okay. So now let's go to the other problem, which is the fixed energy problem. So that Rabinowitz Floer homology that's Morse homology for now H superscript H, for the one with the eta. And as in the previous approach, as by Floer, we can also come up with a gradient flow equation for this AH, again just using this L2 metric. So we have a gradient flow equation. So that's V eta. Now we have both. The loop is flowing and the Lagrange multiplier is also flowing. So we have so this V is again a map from the cylinder to M, and the Lagrange multiplier is a map from R to R. And the equation is the following. So we have first part, we just differentiating with respect to the loop. We get, as before, just with the Lagrange multiplier in it. So dTV minus eta xh of V equals 0. But then we also get the equation for the Lagrange multiplier. So that's ds eta equals mean value of H. So that's the gradient flow equation for this Rabinowitz action functional. And again, so to get the well-defined Rabinowitz Floer homology, one needs compactness for this equation. And here, now we have similar problems as in the case before. We have also, you see also this is first it's basically a holomorphic curve equation, but now there is an additional problem, since you see we have also this Lagrange multiplier eta flowing. And eta, the Lagrange multiplier eta itself, this is a real number, and we need, in addition, establish a bound on this Lagrange multiplier to get compact. Right. So this these are flowing loops. Yeah, right. So the period here is always 1, but as you've seen the equation, so we have at the critical points they have still period 1, but we have the eta in front of the xh, and then you have to reparameterize it. So at the critical point equation you have to reparameterize to get the period orbits of period eta. But so here problem is to get bound on the Lagrange multiplier, and this so in general, this I think fails. But there are, if we have some condition on this energy hypersurface, then we can actually prove existence of a uniform bound on this Lagrange multiplier, a bound which only depends on the asymptotic datas, the critical points for this gradient flow line. So we have also the well-definedness of this Rabinowitz Floer homology. This is depends on this energy hypersurface and on M. Rabinowitz Floer homology. This relates to a bound, or to the compactness of this equation star star, and this relates to a bound on eta along solutions star star. And so this bound is established in the following. So the first is if sigma is of restricted contact type. So then if that means that lambda xh to sigma is bigger 0, then we can prove this bound and get well-defined Rabinowitz Floer homology. So that was done with Zillibeck. So, for example, for mechanical Hamiltonians are just Hamiltonians consisting of kinetic plus potential energy. Sigma is the energy hypersurface. This is H inverse of 0. So for example, for mechanical Hamiltonians, Hamiltonians consisting just of kinetic plus potential energy, this is always the case. But this restricted contact type condition is usually not the case, and it does not need to hold in the case of a magnetic field. And so then later on we improved this with Gabriel pattern 9. So later on we proved that we can also define Rabinowitz Floer homology in the case where sigma is either stable or virtually contact. And I just want to say that these conditions are conditions which are often satisfied in the case where we have a magnetic field. Lambda is a primitive of omega. So omega equals d lambda. So these are conditions often met by magnetic Hamiltonians. So that was Zillibeck and pattern 9. So that's on well-definedness of Rabinowitz Floer homology. Then let me go to computations. So No, it basically means that it's of restricted contact type on the universal cover with some bounds. And this, for example, for weak magnetic fields, and there is a well-defined notion. This means that the energy above money-critical value for weak magnetic fields, they are always energy at the surface are always virtually contact, but they often fail to be of restricted contact type. So this condition comes from the area of magnetic fields. So let me come to computations. And so the first is when N is, and G is a closed Riemannian manifold, and M is just the cotangent bundle of N, and sigma is the unit cotangent bundle, so that's the cotangent vectors of length 1 in P star N, the unit cotangent bundle. And then so the first computation is that in this case, this Rabinowitz Floer homology for S star n, T star n, this is basically given by two copies of the homology of the free loop space of n. So it's H star of Ln, so Ln is just the free loop space of n in positive degrees, and it's H1 minus star Ln in negative degrees. So this was proved independently by Abondandolo Schwarz and Beck and Wancha, and this result could be strengthened to the case where we have a weak magnetic field. So again, above minus critical value, this still continues to hold. So this was generalized to case of weak magnetic field. So this generalization was first by Will Mary, and then by Yang-Xin Bei found the alternative proof to generalize this result, the case of a weak magnetic field. So that's the first computation, and the second is, so here it's very big, we have a lot of homology. So the other one is we have nothing. So then if sigma in M is displaceable, i.e. that exists compactly supported time-dependent Hamiltonian such that the flow, the time 1 flow of F displaces sigma from itself, time one map, the flow, then the Rabinowitz Floer homology of sigma n is just 0. That was with Symplectic. And let me explain a bit about why this second theorem is true. And this comes from the theory of global perturbation of Hamiltonian systems. The idea of two, these are from global perturbation theory of Hamiltonian systems. And in this global perturbation theory of Hamiltonian systems, so what you ask is, you're looking for leafwise intersection points. So, what are these leafwise intersection points? So, assume again sigma is just the energy hypersurface, and then by preservation of energy, and sigma is foliated by the flow phi th of xh. So we have sigma, and then we have a point x on sigma. Then we can look at all the points which can be attained by the flow of h. So that's the leaf. So if x in sigma, then the leaf through x, this is just Lx, this is phi th of x, t in R. And so definition, so x in sigma is called leafwise intersection point. For f, if the one flow of f of x lies again in the leaf through x. So for example, if you think of this Hamiltonian system as the restricted three-body problem, and now there comes some perturbation, maybe some comet, then after this comet comes, then your satellite may go out of your energy hypersurface at all, so energy does not need to preserve at all, but leafwise intersection points are very special kind of solutions. They are solutions where not only your satellite comes back to the energy hypersurface, but the system is basically unchanged. So geometrically it looks like this. So we have here is this leaf, here is this x. Now the comet comes, and so everything goes crazy. But then after this perturbation vanishes, then the satellite just propagates on the orbit he was already before. And the
when you separate F signal from itself, is there no bound on the size of F?
F is compactly supported.
Right, but the max or the oscillations in boundary?
So here, here you can. So this is the so-called displacement energy. So the oscillation of this F, this is then you take the displacement energy of sigma is the minimal oscillation you need to displace it.
So that's the normalization. You normalize the time rather than the...
Right. Yes. No, it actually means no. There are actually many. Since eta, this Lagrange multiplier can also be 0 and negative. So we have a bit generalized periodic orbits. We have also constants where eta is just 0, and we have orbits traverse backwards. And so actually this vanishing of Rabinowitz Floer homology implies existence of non-trivial periodic orbits, since if there would be no non-trivial periodic orbits, there would be just the constants, but the constants correspond to the energy hypersurface. So in this case, the Rabinowitz Floer homology would be just the homology of the energy hypersurface. So this vanishing result gives you, in this displaceable case, gives you this Weinstein conjecture for the displaceable case. So a possible way to prove this Weinstein conjecture. So that's Levi's intersection point, and now there is a variational approach to Levi's intersection points via Rabinowitz action functional. And this approach, this was with Alders, and then later on, Zhongsu Kang also studied this in more detail. So we consider perturbation of Rabinowitz action functional like that. So AHF from L times R to R. So AHF of V eta is just AH V eta minus integral 01 F VT T. And so in general, critical points of this perturbation are a bit ugly, but what we can always do is we can reparameterize H and F so that between time 0 and 1/2 we have just switched on H, and in between time 1/2 and 1 we have just switched on F. And then what one can check is that critical points of this correspond precisely to this. So they first flow with the flow of F, and then they flow back with the flow of H. Then so after the parametrization of H and F, we get some correspondence that if V eta is a critical point of this perturbation, then P of 0 is a Leibniz intersection point for F. And then using this fact we can prove the second assertion, namely if it's displaceable, then we just look at this perturbation. Then if it's displaceable, and in particular no Leibniz intersection points anymore, so there are no critical points at all, and so therefore this Rabinowitz Floer homology just vanishes. And now time is over, so thank you very much.